let us start this lecture with the thought process given by Max Planck, who states that we have no right to assume that any physical laws exist, or if they have existed up to now, that they will continue to exist in similar manner. What a profound statement is given by Max Planck. And we always look at the laws as a gospel of a Bible or a Quran, but however, we need to always keep in mind that those are subjected to scrutiny. For example, in the last lecture, we discussed about 4 laws of thermodynamics. Of course, we started with the various definitions and concepts about thermodynamics. For example, the control mass system, control volume system, and also we have talked about an isolated system. Then we discuss about various other concepts like equilibrium. I call that a system will be in equilibrium dynamically only when it can be in equilibrium mechanically and chemically and thermally, and also in the phase equilibrium must be existing, then only it can be said to be in thermodynamic equilibrium. And then we discuss about other concepts like kind of what you call the equilibrium equilibrium concept we discuss about. Then we moved into the laws of thermodynamics. As I told that J.P. Joule, who conducted series of experiment for over 4 years and put forward a law which is known as the first law of thermodynamics. And we states that whenever a system undergoes a cyclic change, however the complex cycle may be, then the work interaction or cycle integral of the work will be proportional to the cycle integral of heat. Then after that we discuss about what you call apply the first law of thermodynamics for a control mass system, which is nothing but d E is equal to d Q minus d W. And this is basically first law of thermodynamics for a control mass system. If you look at in this case, this E is basically the total energy, and which will be consist of both macroscopic and macroscopic form of energy. Whereas, this macroscopic form of energy, which we always put in terms of internal energy, and macroscopic form we are considering only 2 kinds, one is potential energy, other is kinetic energy, but beside this there are several other forms of energy as well. And keep in mind that energy is the property of the system, whereas the heat interaction and the work interaction is basically not the property of the system, rather is considered to be energy in transit. Then we derive an expression for control volume system, right, and which we will be using for analyzing the propulsive devices. Then we moved into second law of thermodynamics, and where we have arrived at a terminology, that is change in entropy is basically equal to del Q by T, which stems from the Clausius inequality. What is Clausius inequality? If you recall, that which states that whenever a system undergoes a cyclic change, however the complex cycle may be, the heat interaction or the algebraic sum of the heat interaction divided by the respective temperature at absolute or the Kelvin is less than equal to 0, and from that we have derived and if you look at ds is equal to del q by T for reversible process. Whereas ds is greater than del q by T is for irreversible process. Now, then, and this equation if you look at is basically valid for control mass system. For control volume systems, we have derived, or not, rather we have stated about a equation which I urge you people to derive it yourself, and if you find difficulties, then we will look at it. And today what we will be doing, we will be looking at the fluid mechanics part and look at how it can be helpful and what are the concepts involved in fluid mechanics, and about how we can use it for analyzing the propulsive devices. Let me ask a very simple question. What do you mean by fluid? Can anybody answer? What do you mean by fluid?
A substance that have a tendency to flow heavily.
Okay. You are saying that which can flow, right? That you call it as a fluid. But let us, before answering these questions, let us look at what are the kind of matter we are having. The matter, if you look at, it is basically is having a solid, and in case of solid, these are the molecules which are quite compact, right, and there is a intermolecular forces which will be there, and it is in a particular order. We know that in case of solid. In case of liquid, what will be happening? These molecules are little apart and they can move the way it can be, or it will be taking the shape of the place where it container, right. Whereas the gas, it will be moving in a very freely as compared to the liquid and the solid. Now, if this is there, like let us say I will apply a force to a solid. For example, if I take this pen and apply a force, what happens to the molecules? It will be trying to resist the force, and however, there might be some deformation which will be taking place. If I remove this force, then what will happen to deformation? Deformation may, it will come back to the original one, right. That means the stress, right, the deformation we call it as a basically strain, which is change in the length in this example per unit length, and the stress which will be experienced by the molecules of this solid object, right, and this stress is proportional to the strain, of course, within the elastic regime, right. Whereas, if I apply the same with the liquid, certain force, what will happen? It will continuously deforming. That means, we can't really say that it is stress. Of course, a stress will be caused by the fluid, stress will be experienced by the fluid molecules, but however, it is not proportional to the strain, rather it is proportional to the rate of strain. Similarly, for the gas which will be happening. So, therefore, we can define a fluid as a substance that it can deform continuously when being subjected to a shear stress at any magnitude, right. In other words, it can flow continuously as a result of shearing action, right, that we call it as a fluid. That means, the fluid can have a more freedom to move around, right, and whenever it is moving around, what is happening? It will be moving, means it will be subjected to a force and it can move from one place to other, and it will be interacting with each other. That means, molecule in the fluid will be interacting with each other, and when it is interacting with each other, then what happens? There will be change in the momentum due to collisions, right. There will be change in the temperature depending on the whether energy interaction is taking place or not, right. Now, if there is a fluid and which is moving around and I want to know what is the summation effect of this momentum which will be taking place. For example, if I take a small cube, right, of 1 centimeter and 1 centimeter, right, and at ambient temperature and pressure, temperature of 298 Kelvin and pressure of 101,325 Pascal, what will be the number of molecules which will be there inside this? Can anybody tell me? What will be the number of molecules? Huh? What is that? That will be around 10 power to 23, right, and 6.023 10 power 23, like large amount of molecule which will be colliding each other, right. And if I will take that and put a kind of a sensor and look at what will be happening to the molecules, or if I put a surface, a sensor whose surface area will be around, let us say 10 what you call 10 mm or something, or maybe 5 mm kind of thing, right. If I take a what you call let me consider a pipe which is having through which the flow is taking place, the pipe diameter is around 10 centimeter. I will put a probe of 1 centimeter or 10 mm, right. So, what will happening to the pressure if I want to measure, right. That means, the molecule will be bombarding over here and then it will be having what you call the surface on which it will be impacting, and then you will get a sensing it and then you get. But now, that is effect what we call it as a macroscopic effect. But however, if I am interested to look at the each molecules how it is interacting, if I take something 10 power to the 23 number of molecules, that means each molecule I will have to track and look at about its mass, how what is each individual velocity, how it is imparting, and then it will be colliding and the force which is being transferred, then the number of equations and what it will be very high, it will be quite difficult. Now, naturally we need not to really worry about it, but how to handle that? That we can handle in a statistical sense, because it is a quite enormous number of equations one can think of. Whereas, when you will go and to a larger scale length, then what we will call, we call it as a macroscopic effect. As I told that you take a probe of something 10 mm in a pipe of 10 centimeter kind of things, and you will be looking at a pressure or a due to the impact of molecules, you will get is what you call, that is known as a macroscopic effect. But when it will be possible, for example, if the pressure is very low, it is not atmospheric pressure, it is a vacuum almost like in a space, then is it the molecule will come and impact that way? Or if I put another question, that suppose my probe is very small, the size is something let us say 1 nanometer, then the molecule will be in angstrom. Sometimes the molecule will be coming and heating, 1 molecule, 2 molecule, maybe 5 molecules, not a large number of molecules. So, how to go about and use it? Because in our day to day life, we will be considering a macroscopic effect, and that macroscopic effect which will be giving rise to a concept known as continuum, right. And what is that continuum? Is basically when matter in the fluid is continuously distributed and fills the entire region of the space it occupies and can be considered as a continuum. Right. If you look at, I will give an example, like suppose in a city we all together, a lot of people live, right, they will be interacting and other each other, and whereas in the village people will be apart, although in certain villages, particularly in northern India, they will be staying in a group. But if you go to the Kerala, where each individual will be staying away apart from each other, maybe 200 meters or maybe 500 meters away from each other, and they are not concentrated in one place, then interaction will be. So, if you look at one is macroscopic, that you look at all the people, and other is a discrete where it will be going on. So, that means we can call it as a continuum when the people are continuously distributed and kind. But when we can call it as a continuum in a fluid mechanics is an important question, has to be answered, because that will give you a macroscopic way, that means all the properties like pressure, temperature, volume, what you call it as a macroscopic way of looking at can be handled. Otherwise, it is quite difficult to handle when you talk about each molecules and how it is working. For that, let us look at the gas, what it will be having. Suppose I say that this one molecule is impacting with another or being plunged into another molecule, there will be a collision, and this distance what we call between the collision traveled by a molecule is known as mean free path, and this molecule can be moving here, there, wherever is getting something, it will be colliding and then transferring the momentum and the energy depending on its motion. So, therefore, this is the one length scale one can think of while talking about whether it is a continuum flow or a other things, right, or whether we can treat the flow as a macroscopically or not. Now, the other which will be coming into is that scale, what is happening, because for example, if I am considering a pipe in which the flow is taking place, and as I told you it is something 10 centimeter, and in that if the fluid is there which is flowing and at certain velocities, of course, in a pipe, and it is move, also the molecule will be colliding and mean wavelength will be very small as compared to the scale. For example, if it is something maybe 1 mm in a 10 centimeter what you call diameter pipe, right. So, naturally it will be much smaller, there will be several collision which will be taking place within the diameter of 10 centimeter. So, then at that point we can call it as a continuum flow. So, therefore, we will define a number which is nothing but ratio of mean free path and the length scale, characteristics length scale, and which is known as the Knudsen number, right. So, if the Knudsen number is less than 1%, right, we call it as a continuum flow. That means, in this case we can look at macroscopically and look at the properties, and we can call it as a continuum flow. But if the Knudsen number is less than 0.01, that is basically 1% and 10%, right, then we call it as a sleep flow. That means, the molecules will be sleeping from where? It will be sleeping whenever it will coming on the solid surface. In our case, in the continuum flow, if the flat plate is there, fluid is there, then it will be sticking to the solid surface. That means, there will be a no sleep condition at the surface of the solid over which it is flowing. And in the sleep flow, then it will be quite difficult to handle, and when the Knudsen number will be between 1% and 1, then we call it as a transition flow, and when the Knudsen number is greater than 1, this is known as a free molecular flow, right. That means, the molecules will be free, separate each other, and you need to look at. And it is if you look at in our applications, of aerospace propulsion, we will be mostly dealing with the continuum flow. But however, when your spacecraft will go to the deep space, then can we really apply? You cannot really apply, but however, if I look at my system, it is a rocket engines or something, then I can say it is a continuum, but outside it will be difficult. And it is a quite a very hot topic even if today, because it is still to be evolved, and there is a very beautiful book written by G. A. Bard, is known as molecular gas dynamics. If you are people are interested in, you can look at that book, and keep in mind that this continuum flow which we will be dealing with will be governed by a number, Knudsen number, and which must be less than 1% or 0.01, and it can be related to what then? Can it be related to certain properties? Any of you are aware about that? It will be related to 2 non-dimensional, rather 3 non-dimensional variables, which I will be leaving for you to look at it. Maybe as we go along, we will discuss, right. And that can be derived by using molecular theory of gases. So, let us look at, like when you talk about this fluid, how to classify the fluid flows, because we will be more interested in the fluid flow in case of these aerospace applications. How? Because how this fluid flow will be helpful? It can be helpful in 2 ways. One way, that whenever fluid is flowing through a duct or over a surface, it will be experiencing what you call certain force will be applied, or certain force or the thrust will be generated. Beside this, whenever we are converting some energy into the thrust force, we need to pass through what you call a mixing. That means, some energy conversion will be taking place, some chemical reaction will be taking place, as we are using the fuel as a energy source, and then there will be some diffusion and mixing will be taking place, right. So, therefore, fluid is very important, fluid flow is very important for our what you call aerospace applications. Particularly, for example, I can have a motion in a pedal cycle, but is it really we need any fluid there? We do not need, we are applying the force mechanically and using. But if I want to travel in the air, or if I want to travel or make a object to move in the water, then naturally fluid flow comes into picture, and if you want to go at a higher speed, then naturally we will have to use the fluid devices. So, therefore, it is very important to understand the fluid mechanics and the concept about it, and as I told that we will be dealing with the continuum flow, where the fluid will be adhering to the solid surface, and as a result there will be some viscous or kind of things which will be taking place. And the fluid flow can be classified into viscous and inviscid region of flow. So, viscous flow is one in which the frictional effects are significant. For example, if there is a solid surface, and let us say this is a solid surface and the fluid is going over it, then what will happen? The fluid will be trying to retard on the surface of the plate or the surface on which it is moving, right. And the friction, if you look at, we all experience friction. For example, if this is a surface, I am rubbing it. So, what I am getting? I am trying to rub it and get a friction, and it is resisting. That means, so therefore, that is the generally the viscous flow is considered only when it is having a frictional effects, which is quite significant in comparison to what? In comparison to the inertia, right. And beside this, there will be some thermal conduction. Conduction means some heat transfer will be taking place, and also the mass diffusion, like in your combustors, where the fuel and air has to be mixed, and then it will be reacting, then you will get transfer this what you call chemical energy into the kinetic energy and other things. So, there also we call it as a viscous flow, but although in fluid mechanics people do not talk about it generally. And beside this, whenever its viscous effect is negligibly small, then we can call it as a inviscid flow, and where the viscous forces will be neglected, can be neglected as compared to the inertial or the pressure force. And keep in mind that we will be using this inviscid flow analysis for our propulsive devices, right, because of the boundary layer which will be coming, we will be discussing a little later on, that will be very, very small. And let us consider that the flow over a flat plate which is having a uniform flow, and then when it is flowing through it, you will see that as it goes, then the flow gets retarded on the surface of the solid. As a result, it is having a fluid the velocity profile, which is is 0 velocity at the solid surface, and it goes on increasing at certain distance along with the y direction. If I say this is the y direction, right, and this will give you basically the resistance or the boundary layer. A layer will be coming into pictures. Let us look at that a visual pictures, or that you can see that this is the velocity profile, and where the viscous flow region is very, very small, and whereas the inviscid flow region is quite large. And wherever it will be, and therefore, we can apply this inviscid analysis for this region, whereas whenever we want to find out what will be the drag or the kind of things, we need to consider this kind of viscous region for analysis. And if you look at the shear stress, we can evaluate at this region. If you look at from this, taking this point here, that it will be shear stress will be proportional to change in the velocity with respect to, this is my normal direction n, and dou v by dou n. And when it is proportional to the rate of strain, then this is tau, it can be expressed as tau is equal to the mu in dV by n, where mu is the dynamic viscosity coefficient. Keep in mind that this will be valid, or we call is for Newtonian fluid, right. That means, the shear stress is proportional to the rate of strain. But however, there will be some other fluid like a viscous fluid, like your what you call lubricating oil, or even in your paste, which are not, which will not be following this Newtonian concept of fluid. But in our what you call analysis, or in this course, we will be restricting ourselves to the Newtonian fluid only, right. Let us look at about the laminar versus the turbulent flow. If I ask a question, what do you mean by laminar? The name indicates that it will be layer by layer, right, and it will be quite smooth and orderly manner the fluid will be there. For example, if I take this flow over a flat plate, you can see that fluid layers by laminar, layer by layer kind of things moving without intermingling with each other. For example, I will give an example. Let us say in an army, the soldiers are moving, they will be moving in a very orderly manner. That means, they are quite disciplined in nature. Some of you might have taken NCC, you will be going in a row kind of thing. So, that you can call it as laminar, and which is and in contrast, the turbulent flow will be quite disordered, it will be intermingling each other. As a result, the velocity or the temperature or the pressure, which are the proper fluid properties, it will be changing with respect to time. And if you look at our in Kanpur the traffic, it will be more towards turbulent. Sometimes I feel it is not turbulent, rather it will be transition, it will be in between kind of region what I have shown. So, in order to talk about this laminar turbulent, we always think about the whether it is the we need to define a number which is known as Reynolds number, which is a ratio of inertia force divided by viscous force, in this case rho V x divided by mu, where rho is the density, V is the fluid velocity and x is the characteristic distance. And this x in case of a flow over a flat plate will be the length from the leading edge can be measured, and mu is the viscosity, that is your basically, and this will be decided by the Reynolds number will decide whether the laminar flow is laminar or turbulent. In case of flat plate, we know that critical Reynolds number will be around 5 into 10 power to 5, whereas for a pipe flow the critical Reynolds number will be around 2300, right. And keep in mind, this is the non-dimensional number which dictates whether the flow is laminar and turbulent, and the transition flow is between the laminar and turbulent. I always feel that give an example, laminar means, and when you look at your mind, particularly when you are a small baby, you do not really bother about other things, it will be in laminar regime. When you are youth, your mind will be vacillating and more confusing here and there, then it will be like a transition, because it is very difficult to predict. Similarly, transition flow is quite difficult to predict. Therefore, lot of research is going on today to understand the transition behavior of the flow. And similarly, turbulent will be the latter edge what one can think of. So, let us look at a flow over a flat plate, and if you look at this is your laminar regime. In this case, as you told that as the x increases, your Reynolds number what to call increases, although the your upstream velocity u infinity is remaining same. So, also the viscosity, because it is the same fluid, and there is a transition region where it will be having a fluctuation. I mean, generally people talk about there is a mark like this that indicates a transition flow. Of course, after that boundary layer although grows, and then it will be turbulent regime. In this regime, there is a viscous sublayer where it will be flow will be almost like a kind of viscous, and then there will be momentum transfer from this region to the wall, which will be taking place. And however, this will be growing, this the boundary layer, which is defined as a velocity of 0.99% of the free stream velocity, because it will be asymptotically velocity will be increasing. So, at that point we define, and keep in mind this is the ad hoc way of doing it, because where we will define, and we have taken as a practically 0.99% of free stream velocity. So, if you look at this is the boundary layer sticking to the what you call the solid surface, and there might be a way where the boundary layer will be separated from the solid surface, and that depends on what? It will be dependent on the type of surface what we are, and also in other words it will be dependent on what? Pressure gradient. So, let us consider a ball here, and in this case this place of course fluid is coming, which is not shown here. In this case the fluid is almost laminar, and then it gets separated and it is recirculated and mingled, and the flow became turbulent in the wake region. This is known as wake region, right. And this flow separation will be dependent on whether the flow is laminar or turbulent, right. And this is a simple ball which I have taken. Now, as I told earlier that in this case the velocity profile is parabolic in nature, and when the pressure gradient increases, suppose I will be having adverse pressure gradient at the downstream, what will happen? The velocity profile will be like that. That means, it become a coming flow will be retarded more in this region as compared to this, because of adverse pressure gradient. Somebody is trying not allowing the fluid molecules to move forward. So, then it will get an inflection point will be almost 0 for certain this thing along the y direction. That means, this is my y direction, this is my x direction, right. So, therefore, as the pressure gradient increase further, what happen, the fluid will be moving what you call towards that, and then it is opposite direction of the fluid. That means, it will be opposite to the x direction, is the negative x direction. Therefore, the flow will be separated, right. So, that means, flow separation occurs whenever there is a pressure adverse pressure gradient occurs in the flow and that may be due to the shape and due to the some other back pressure and depending on the situation. Now, if you look at the laminar flow will be causing more separation in a body as compared to the solid, comparison to the turbulent flow. I will take one example. This is a smooth sphere like a ball, you can say, and flow is laminar here, and of course, the flow becomes separated, and this of course, the like having a thick wake region. But if I make this ball as a dimple like a golf ball, right, this is intentionally made some dimple like this kind of shapes being made, indentation kind of thing, and then what happened, this became transition, and then that flow separated like became turbulent. However, the separation became occurs at the downstream of the ball as compared to the here, right. It occurs very very early, right. And however, the as a result the thick the wake region is very thin as compared to the thick here. So, what it indicates? It indicates the turbulence retards the separation of the flow. So, if you look at turbulence, always people wants to avoid, right, in some situation, but here it is advantageous. That means, whichever is a negative things can be converted into a potential tool for achieving something. So, which is very important in life as well. So, we need to understand ourselves and find out ways and means of using those negative aspects for getting a positive thing. So, question arises, we are discussing about the viscous or inviscid fluid, then we talk about laminar and turbulent, and what we are doing? We are looking at basically the friction effect, and we have seen that it is basically generating a shear stress, right, and then this flow separation, other things are coming, but is there any other things it can do? In other words, what does friction do apart from generation of shear stress? Can anybody tell me? It will be generating heat, right. Under what condition it can generate heat? Relative motion. Why it will really generate the heat whenever there is a relative motion? What is the reason? Momentum. So, momentum what? Momentum means it will be a force. So, how it will come into picture? Right. So, that means if the rubbing of the surface is taking place, there will be some kind of a dissipation, right, which we will be discussing about it. Beside this, what else it can do? Let us consider the flow separation in the ball, what we are discussing here. Fluid is coming over and then it is get separated at certain region, this is separated flow, right. And whenever this flow is separated, what happens to the pressure in the wake region? It is being reduced, right. Okay. And when it reduces, then what will happen? It will be trying to drag this ball along with the fluid more as compared to the what you call apart from dragging due to the friction, because if ball is moving, it will also due to the friction it moves, right. So, that means it will be helping in that, and if I want to reduce this drag force, right, it will be dragging. That means, dragging can occur due to what? Due to two things. One is your skin friction due to the viscosity or due to the this thing, and other is due to the separation of the flow, right. There will be a pressure drag also. But if I want to what you call reduce the drag, then what I will do? I will make the body to be streamlined. That means, the shape of the body in such that the flow will be gliding over without really much way to separate from the solid surface. However, in this case I have shown there is a little surface here. So, if you look at, you are getting the drag due to the skin friction and also pressure drag. So, to summarize, the types of the drag will be, one will be skin friction drag and other is the pressure or the form drag. So, the total drag will be skin friction and form drag. Keep in mind that always we want to design a surface in aerospace like a foil kind of things is basically streamlined body to reduce the pressure drag, right. But is there any place where we will be using a blob body, like if you look at this is in this case I have written here as a blunt body, even we known as a blob body, which is a non streamlined body. Can we really use somewhere? Space shuttle. Re-entry vehicle will be streamlined body you always use, right. Of course, that depends upon the what kind of wave and other interaction, because the streamlined body is there, it will be different. Okay. But what I am saying is we can use a non-streamlined body in some place which will be beneficial for achieving certain thing. For example, blob body is a non-streamlined, like I have put a circular or a flat plate over the flow. Like for example, if I take a what you call, if I take a blob body over a flow, just a flat plate, let us say this flow is coming this way, right, and I put a body like this, then what will happen? There will be recirculation, region, and this is a plate, vertical plate, right. Can I use somewhere this to achieve something in my propulsive devices? We will see that we will be using this for in combustor for getting a fuel air mixing, better mixing, and also stabilizing the flame. So, whichever is the problem in some place, it can be used as a solution to overcome the problem. So, that is a very important point, one should look at it, and we will be using these concepts in while talking about the propulsive devices. And as we have already discussed, there is a some of you told that because of whenever the vehicle or a body is moving or fluid is moving at a high speed over a body, I mean it can be vice versa, then what will happen? There will be lot of kinetic energy which will be converted into the internal energy. That means, aerodynamic heating which will be experiencing by the solid surface due to high speed flow over like airplane or missile or a spacecraft, to give some example, or any other surface whichever is coming, and then that heating has to be taken care, otherwise your vehicle like will be in trouble. For example, if a aircraft which is moving at a very high speed, keep in mind it is having a delta wing which says that it is applied, it is can fly at a very high speed. In the nose region you will get a very high heating portions, and so also in these edges of the delta wing, right, and some places here as well. So, that means you need to take care of these whenever you are talking about or designing a aircraft or any other things. And similar situation may occur in your gas turbine application, particularly turbo machinery, when you are going for a kind of a high speed or the flow over a turbine blades kind of thing. So, therefore, one has to worry about this aerodynamic drag. keep in mind that kinetic energy in this case is converted internal energy, and as a result there will be increase in temperature, and which is known as viscous dissipation, because it will be dissipated, you cannot get it back. And one has to also take care of this thing when designing any devices of that. So, now we have talked about basically internal versus the external external force, and we need to understand what do we mean by internal flows and external flow. The flow of an unbounded fluid over a surface, like a flow over a flat plate, flow over an aerofoil, flow over an aircraft or a missile, all those things will be external flow, right. And the flow in a pipe or a duct, particularly example like a nozzle, air intake in turbo machines, right, will be internal flow, right. But however, in case of the what you call a turbo machine, which I have shown, there is having a rows of blades, right. If you look at the flow is here is basically internal flow. However, on the surface of it we can call it as a what you call external flow kind of things, because if it is far away from, that means blades are being far away, then only, otherwise we will call it as a internal flow, right. So, whereas the external flow, if you look at, if I take a turbine, wind turbine, right, which is also one another kind of turbo machine, then naturally the flow will be external in nature. So, what we have will be discussing now basically the steady and unsteady flow, and steady flow, that in which there will not be any change in properties at any point of time. For example, if the flow is taking place in a nozzle, which is shown here, at the time 4 am, the velocity is 5 meter, let us say at this point, right. If I consider that at the same point and at the time 11 pm, that means several hours have been passed, the velocity is almost 5 meter per second. It can't be, you cannot say it is exactly 5, if it is 4.9 or maybe 5.1 on some average, you can say it as a steady flow, right, and which is likely to occur provided if you keep the flow is the same continuous manner. You may ask a question, suppose when it will occur, if my engine is in the test bed and there is a nozzle through which flow is taking place during the hour of operation, it will be remaining constant provided I am keeping it as a constant. If I will throttle it or vary it, then naturally it will be different. So, whereas the unsteady flow, in case there will be what you call change at a point with time, that means the properties will be changing at a particular point in time. For example, if I look at this what you call a rotor or blades which is rotating, if you look at each point, it is moving, so that it will be different. That means, if I consider a point and then look at the properties like pressure, temperature, velocity, it will be changing, right. Of course, in this case it will not be, temperature will not be changing, but velocity and pressure will be changing with respect to time. So, therefore, we can call it as an unsteady flow, and there is also the uniform flow, in which case the velocity or the fluid properties will not be changing along a cross sectional area, right, over a specified region. For example, in this case these are the places I am keeping the what you call fluid velocity as a uniform, you can see from these streamlines. Similarly, it is very important whenever we need to identify where the flow is uniform. We will be doing that particularly when we will be deriving an expression for a thrust force, then we need to identify a uniform velocity, that means because to have to simplify our analysis. In this case, if we look at, this is a car, the flow is taking place over it. If you look at, these are the streamlines which is being not curved one, which indicate that is uniform. But if I go for away from this, you will find the flow is uniform. Similarly, if I go away from this, the wake region of the car, this is the wake region, then I will get uniform. And of course, the inlet you can have a uniform, provided it is in a wind tunnel or somewhere. You cannot get a uniform flow very exactly or accurately when it is moving, because there might be several other things vehicle will be coming. So, we need to understand this very important aspect, because we will be looking for using it for a simplifying analysis, right, in some several places. So, there is also a known as periodic flow, like where unsteady flow will be there, but the flow oscillation will be varying about a steady mean. For example, if I am keeping this RPM of the blade at a constant, I am looking at a particular thing, I will find that as the RPM is remaining constant, it will be coming periodic, right. It will be coming and going, coming and going. So, that way it will be periodic in nature, and which will be useful particularly when you are analyzing the turbo machinery. And in gas turbine engines, the turbines, several components like turbines, compressor, nozzle, air intakes can be considered to be operated under steady state condition, particularly under level flight of an aircraft. Suppose you are flight leveling, not like your fighter aircraft, where you need to change, change means you will have to need the change the thrust as well. So, the condition inside the gas turbine will be changing. So, therefore, we cannot, but however, in the very simplifications or in under certain situation like level flight, one can consider to be a steady flow, and which we will be using most of the times unless otherwise being stated. So, with this we will stop over. Before that, let us summarize what we have learnt. Can anybody tell me what are the things we have discussed till now? Okay, let me tell that, like we have started a discussion about the fluid mechanics, defining how it is different than the solid, and then we talked about a Newtonian fluid and how it is different than the non-Newtonian fluid, and then we discussed about continuum concept and how it will be useful, and it will be differentiated from the other flows by a number known as Knudsen number. Then we moved into what you call the laminar and turbulent flows, and then we have looked at the effect of the viscosity, and apart from the what you call the viscous effects or the shear stress being generated, then it can also produce the drag, and then we talk about the total drag is basically sum of the skin friction drag and pressure drag. Then we talked about aerodynamics, heating effects, and then we looked at steady and unsteady flow. In the next class, we will be discussing about various aspects of fluid mechanics, then we will be looking at governing equations, then we will be moving to the compressible flow, which is quite important for analyzing the your propulsive devices. Is there any other question you people are having? You can ask me. Okay, thank you very much.